In this section, we are going to discuss one of the methods for unambiguously describing organic molecules that is commonly used by what I'm calling real chemists. And I mentioned this briefly in the previous section. It is a way of describing organic molecules and describing the attachments. It's called a skeletal structure. So the idea is that most professional chemists actually draw organic molecules using this convention, which is called a skeletal structure. On this slide, I'm going to describe the rules. And if you're not familiar with this, which many of you may not be, it may seem a little bit weird, especially without giving you examples on this slide, but please bear with me. It's worth it just to introduce the rules at first. So one of the rules is that carbons are usually not drawn out. The letter C is usually not used when you're drawing the organic molecule. The reason is that organic molecules have a lot of carbons, so you can save yourself a lot of time if you just don't write the letter C. The way that you say that there is a carbon in your molecule is you imply them as either the corner or sometimes the end of a line. So usually you don't draw the letter C. I'll try to point out the occasions when you might actually draw the letter C. The bonds between the atoms are actually drawn out. This is one of the things that you do actually physically draw out. So you'll use a single line for a single covalent bond, double line for double covalent, triple line for triple covalent. So you draw the bonds out. You tend not to draw the letter C. The third rule is that the hydrogens, again, are usually not drawn out. Usually organic molecules have so many hydrogens that it becomes a relatively gigantic pain to draw all of the hydrogens. Even if you're using a condensed structure, it can become a pain. So you don't draw the letter H as well for the most part. They are usually implied. The hydrogens, the implication where the hydrogens are in your molecule is probably the hardest part for the students, but I'll try to take you through that in the subsequent slides. And then the idea is that you're not usually drawing the letter C, you're not usually drawing the letter H. If your organic molecule has other types of atoms in it, if it has oxygen, nitrogen, whatever, you actually do draw those elements out. So every other type of element is drawn out. So, as an example, this is C4H10. This particular version of C4H10 is called butane. So hopefully you can refer back to a sheet of paper that you may have next to you to look at that and confirm that that is butane. And this is an expanded structure for butane. And just to refamiliarize you with this is the condensed structure for butane. We're treating each carbon as its own little chunk, its own little unit. The leftmost carbon has 3 hydrogens, etc., etc. That is the condensed structure for butane. This is the skeletal structure for butane. And as I mentioned on the previous slide, the carbons don't get drawn out. They are implied as ends and corners on a line. So here's an end. What that means is there's a carbon there. Here's a corner. There's a carbon there. Here's another corner, a third carbon, and here's the other end. That's the 4th carbon. You don't draw the letter C in any case, and hopefully you can see that this is an even simpler way of drawing the condensed structure or drawing the expanded structure. So carbon, 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 carbon. The other thing that you can ask is, well, where did the hydrogens go? The hydrogens are also implied, and it's a little bit strange in how they're implied, but this carbon that is implied at this end, every carbon, if you remember from the rules earlier in this unit, every carbon has to make 4 bonds. So there's a carbon that there's an invisible carbon here that I'm sort of drawing out. And you can see that this invisible carbon is making 1 covalent bond that you can see. It's making this covalent bond that's drawn out. But we said that every carbon has to make 4 covalent bonds. So there must be 3 other bonds that you cannot see. Those 3 other bonds are always implied to be to a hydrogen. So even though you can't see any H's here and you can't see any bonds to invisible H's, the bonds are also sort of implied. They are invisible. This carbon here has 1 bond that you can see, and it must have 3 others that you can't see, and those 3 others have to be to hydrogen. This carbon here, this invisible carbon on this corner, is making 2 covalent bonds that you can see. It's making this one, and it's making this one off to the right. Because this invisible carbon is making 2 covalent bonds you can see, but it has to make a total of 4, there must be 2 covalent bonds that you cannot see. And those 2 covalent bonds that you cannot see must be to hydrogen, which means there have to be 2 hydrogens attached to this carbon that is sitting on the corner here. And that can be confirmed by looking at the condensed structure. Same thing with this invisible carbon. You can see this carbon making 2 covalent bonds, so there must be 2 invisible bonds that you can't see in addition to this carbon. So there must be 2 hydrogens attached here. This invisible carbon at the end is making only 1 covalent bond that you can see, so there must be 3 hydrogens attached there. So this is an example of a skeletal structure for butane. It's a little bit weird, but once you get used to it, I think you'll appreciate the fact that this is much easier to draw than either of these 2 versions, either of these 2 cartoon versions of butane. Now, I said there are some exceptions. Sometimes you draw the letter C, sometimes you draw the letter H. The exceptions, for the most part, some people like to draw the letter C at the end of the line. So sometimes you will see butane drawn like this, that the carbons are not drawn only when they are corners, but they are drawn at the very end of a chain or a line of carbons. So sometimes you'll see the carbons drawn out explicitly at the very ends of the line, and usually when they are drawn out, you will draw the hydrogens that are attached to those carbons. So in this case, we're actually drawing out the carbon at the end. It's not invisible, and because of that, we're going to make the hydrogens visible as well. And the same thing at this other end. This is just another way of drawing the skeletal structure of butane. It's an alternate version of the skeletal structure that I'm circling up here. Some people like this. They think it's more aesthetically pleasing. Some people like this. I tend to prefer the very minimalistic version. The other time that you draw hydrogens are when they are attached to something that is not a carbon, and I will show you an example of that in a little bit. But if this is taking a little bit of getting used to, you might want to replay this, and I will show you a couple of other examples. This is hexane, 1, 2, 3, 4, 5, 6 carbons. This is the expanded structure for hexane. This is the condensed structure for hexane, and as you can see, this is the skeletal structure for hexane, because there are 6 carbons implied, 2 at the ends, 1, 2, and then there are 4 corners, 1, 2, 3, 4. So a total of 6 carbons. This is just the skeletal representation of hexane. And eventually these sort of tend to look like zigzag lines or Charlie Brown's shirt, if you're familiar with Charlie Brown. And again, an alternate way of drawing the skeletal structure for hexane is to actually draw the carbons at the very end of the chain of carbons. So that is a very short introduction to skeletal structures. Now that we have the beginnings of skeletal structures under our belts, let's talk about this version of C4H10. This is the alternate version of C4H10 that we described earlier in this unit. How do you represent this using a skeletal structure? First, I just want to show you, this is the condensed structure for this alternate version of C4H10. You're treating each carbon as a chunk, and you're drawing out every carbon and every hydrogen. This is how you would draw that version of C4H10 using a skeletal structure. Again, there are 4 carbons, 1 at each of the 3 ends. Here's 1, 2, 3, and there's 1 in this middle corner. So this is another representation of this molecule or this molecule. And again, the hydrogens are implied. There's an invisible carbon here. You can see it making 1 covalent bond. There must be a total of 4, so this invisible carbon has to be making 3 invisible covalent bonds that you can't see, and those 3 invisible bonds have to be to hydrogen, so there must be 3 hydrogens attached to this invisible carbon. The same thing for this carbon, the same thing for this carbon. If you look at this central carbon, this invisible carbon in the center, you can see it making 3 bonds, 1, 2, and 3 off to the right. And because each carbon has to make 4 bonds, this invisible carbon must be making 1 invisible bond to a hydrogen. So there has to be 1 additional hydrogen attached here that you can't see. Even though you can't see it, it's there, and you can see it in the condensed structure. And again, just to show you an alternate, sometimes people will draw out the carbons and the hydrogens at the very end points in a skeletal structure. So this is an alternate version of the skeletal structure of this molecule or this molecule. And you can see that in this case, the skeletal version is not much different than the condensed version. The only difference is that you're not drawing this hydrogen in the center. It's implied to be there, but you don't draw that one out. So either of these is a perfectly acceptable skeletal structure. Again, I tend to favor this this type of version just because it's actually easier on the hand once you get used to the rules. This is an example of showing where the skeletal structure becomes advantageous to the person who actually has to draw it out. This molecule here, this is an organic molecule. This is the active ingredient in Advil. If you've ever taken Advil for pain, this is ibuprofen. This is the condensed structure for ibuprofen, and you can see that you're treating every carbon as a chunk. There's a CH3 attached to a CH, etc., etc. There are some double bonds here, double bond there, etc., etc. There's an oxygen there, and O8, an oxygen, and a hydrogen there. This is the skeletal structure for ibuprofen. Again, pretty much the carbons are not drawn out. The hydrogens are implied. There should be 3 hydrogens over here where I'm circling, 3 as well here. There should be 1. Eventually you'll become accustomed to figuring out how many hydrogens are attached to each endpoint in each corner. There are double bonds here, just like there are double bonds there. Double bond, etc., etc. There is a carbon double bonded to an oxygen. This corner, there's an invisible carbon, and it's double bonded to an oxygen. If you remember, one of the additional rules about skeletal structures is that anything that is not a carbon or a hydrogen has to be drawn out. So you have to draw out the oxygen atom here. There's a carbon attached to an oxygen by a single bond, and that is implied here, and this oxygen also has a hydrogen attached. The other thing that I said is that the hydrogens usually are drawn if they are attached to something that is not a carbon. In this case, the hydrogen is attached to something that's not a carbon. It's attached to an oxygen, so you actually draw out the hydrogen atom in that case. So again, skeletal structure for ibuprofen. At this point, I think it's probably worthwhile to end this section by giving you an example to work on. So this is a skeletal structure of a molecule that I pulled off of the internet, and usually I will show this to the students in my on-ground class, and I'll ask the following questions. And you can pause at any point and basically try to answer this on your own. It's probably worth it to draw this out on a sheet of paper and then basically say, how many carbons are in that molecule? How many hydrogens, how many oxygens, and once you figure all of that out, you can write the simple molecular formula for this particular molecule. So you can pause now and do that, and I will show you how to answer those questions in a minute. So the first thing that I would do, if you're just beginning and having difficulty, is I would actually draw out the molecule and then draw the letter C for each implied carbon. So there's a C at the end. So you draw C. There's a double bond. That's what this means here. So this carbon is double bonded to this carbon over here. And there's a carbon at every corner and every end. So there's a carbon in this corner, a carbon at these 3 ends, and then there's a carbon in the center here. So now we can count how many carbons there are. There are 1, 2, 3, 4, 5, 6, 7. 7 carbons. Then how many hydrogens? This tends to be the most difficult because you have to do a little bit of subtraction, but this carbon over here, you can see it making 1, 2 bonds because this is a double covalent bond. Every carbon has to make a total of 4, so this carbon is making 2 invisible bonds to hydrogens. So there must be 2 hydrogens attached there. There they are. This carbon over here is making 1, 2 bonds from this double bond. It's also making a 3rd bond that you can see, so there must be a 4th invisible bond to a hydrogen. This carbon as well, 1, 2, 3 bonds that you can see. There must be 1 additional invisible bond to a hydrogen. This carbon here, you can only see it making 1 covalent bond, so there must be 3 additional invisible bonds to hydrogen. Same with this carbon over here, same with this carbon down here. This carbon in the center is making 4 bonds that you can see. It's making 1, 2, 3, 4. Because of that, there can't be anything else attached to this carbon, so there are no hydrogens there. So we can count up the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and don't forget this hydrogen over here that's attached to the oxygen. That makes 14. So 14 hydrogens. How many oxygens? Well, that's relatively easy. They have to be drawn out. So there's only one oxygen. So the formula for this particular molecule, the simple molecular formula, is C7H14O. And that's basically it for skeletal structures. You're going to see a lot in the rest of this unit, but that's our introduction.